Hi friends, welcome to Incredible Learning Experience, Jnana Learning. So today's our topic is Fundamental Digital Logic. So this lecture includes Introduction to Digital Systems, Digital Logic States, Boolean Algebra, Boolean Logic Operations, Boolean Addition and Multiplication, Logic Rules, De Morgan's Theorem, Forms of Boolean Expressions and Digital Logic Gates. So first is an introduction to digital system. So today most of the modern electronic devices are based on digital electronic principle. That is, digital systems depend on pulses of electricity to make a particular circuit work, which means that if current is present in a circuit, it is represented as 1, and if current is not present, it is represented as 0. So this is the basic principle. Now moving on to digital logic states. In digital logic, only two voltage levels or states are allowed. That is a logic 1 or 0, high or low, true or false. So these are the states allowed in digital logic. And these states are represented in Boolean algebra and truth table by the numbers 1 and 0 respectively. That is 1 for the high state and 0 for the low state, like that. Commonly, the binary 0 and 1 are represented by logic voltage levels 0 volt and plus 5 volt. Okay, so that's about digital logic states. Now here there is a term you have noticed, that is Boolean algebra. So next we are discussing what is Boolean algebra. So Boolean algebra, it is a special symbolic mathematical language used to carry out logic operations. And it was developed in the year 1854 by George Boole. And in Boolean algebra, variables take only two possible values, that is either 1 or 0, and it is a language used for performing binary logic operations. And in Boolean algebra, it defines constants, variables and functions to describe a particular binary system. So we will see what is a Boolean constant. So there are two constants, that is one is 0 and other is 1. 0 represents the false state and 1 represents the true logic state. And coming to Boolean variables, it is similar to the other variables we are commonly using. That is, these variables take either two values 0 or 1 at different times, and the variables can be represented by symbols such as a, b, x, y, etc. Now the third one, that is Boolean function. So it is an algebraic expression formed with Boolean variables, the operators or, and not, and an equal sign. Okay. Now each of the elementary logic function is represented within the Boolean algebra by a unique symbol. So that's about Boolean constant, variable and function. So now we move on to the Boolean logical operations. So mainly there are three operations: logical AND operation, logical OR operation and logical NOT operation. So the three functions AND, OR and NOT, the symbols corresponding to these three functions are dot, plus and bar, and the expressions are represented as C is equal to A dot B for AND function, C is equal to A plus B for OR function, and Z is equal to A bar for the NOT function, where A and B are the inputs and C is the output. So in logical AND operation, the truth table is given, that is the output C will be in such a way that if both the inputs are 0, output will be 0. If inputs are 0, 1 or 1 or 0, output will be 0, and if both the inputs are 1, output will be 1. And the second case, that is the logical OR operation. So in that case we have two inputs A, B and output C. In that case, if both the inputs are 0, output will be 0, and for all other cases the output will be 1. And in logical NOT operation, it is just an inversion operation, that is if input is 0, output will be 1, and if input is 1, output will be 0. So that is about Boolean logic operations. Next is the Boolean addition and multiplication. So Boolean addition, the basic rule of Boolean addition is that is 0 plus 0 plus 0, the output is 0, 0 plus 1, result is 1, 1 plus 0, result is 1, and 1 plus 1, the result is 1. So have you noticed any similarity with the logical operations that we have already explained? Yes, the Boolean addition is same as logical OR operation. And coming on to Boolean multiplication, the basic rules of Boolean multiplication methods are 0.0 is equal to 0, 0.1 equal to 0, 1.0 is equal to 0, and 1.1 is equal to 1. And Boolean multiplication is same as that of logical AND operation. Okay, so that's about addition and multiplication. Now we move on to some important rules, that is logical rules. So rule number 1 is inverse law, and inverse law states that a plus a complement is equal to 1, a dot a is equal to 0, and a double complement is equal to a. Rule number 2, that is identity law, which states that a plus 1 is equal to 1, a plus 0 is equal to a dot 1 is equal to a, and a dot 0 is equal to 0. Rule number 3, that is absorption law. It states that a plus ab is equal to a into a plus b is equal to a. And rule number 4, that is idempotency law. It states that a plus a is equal to a and a dot a is equal to a. Rule number 5, that is commutative law. It states that a plus b is equal to b plus a and a dot b is equal to b dot a. Rule number 6, that is associative law. It states that a plus b plus c is equal to a plus b plus c, and a dot b dot c is equal to a dot b dot c. So the position of brackets are important here. Now rule number 7, that is distributive law, which states that a dot b plus c is equal to a dot b plus a dot c, and a plus b dot c is equal to a plus b into a plus c. Rule number 8, that is consensus theorem, which states that a dot b plus bc plus a bar dot c is equal to a dot b plus a bar dot c. And the last rule number 9, that is transposition theorem, which states that a dot b plus a bar z is equal to a plus z into a bar plus b. So these are the different rules. And next we want a theorem, that is De Morgan's theorem. Now De Morgan's theorem states that theorem number 1 states that a plus b whole complement is equal to a complement dot b complement, and theorem number 2 states that a dot b whole complement is equal to a complement plus b complement. So there are two theorems which is known as De Morgan's theorem. It is very important in logical minimizations. So the rules which already explained under De Morgan's theorem helps to minimize different logical operations. Okay, so next is the forms of Boolean expression. So mainly there are two forms of Boolean expression which are called as SOAP form and POS form. SOAP form means sum of products and POS form means products of sum. So first one, that is SOAP form. In SOAP form, the product terms are formed first and then they are summed together. Okay, and each of the product terms in the standard SOAP form is called as min term. For example, a bar bz plus abc bar plus abc. It is of the type SOAP form, which means that the product terms are first considered and then they are summed together to form the SOAP form. In product of sum form, the sum terms are formed first and then the products are taken. Okay, and each of the sum terms in the standard POS form is called as max term. So for example, a plus b plus c into a bar plus b plus c into a plus b bar plus c. So here a plus b plus c, a bar plus b plus c, a plus b bar plus c are the sum terms. They are first considered and then the products of that particular terms are taken. So these are the two forms of Boolean expression. Now we move on to digital logic gates. Okay. So logic gates are the fundamental building blocks of digital circuitry. It is an element that takes binary input signals and produces an appropriate binary output, which depends on the states of the inputs given. Now the logic gates are mainly classified into three as fundamental gates, compound gates and universal gates. The fundamental gates are AND gate, OR gate and NOT gate. Compound gates are NAND gate, NOR gate, XOR gate and XNOR gate. And NAND gate and NOR gates are actually universal gates. So we move on to the first gate, that is AND gate. So in AND gate, the output of an AND gate is defined as it is true if and only if all of the inputs are true. Actually, it performs a logical multiplication, and the Boolean expression for AND gate is given as Q is equal to A dot B, where A and B are inputs and Q is the output. The symbol of an AND gate is given over here, and its truth table defines that if both the inputs are true, then the output will be true. That is 1. For all other states, the output will be 0. So that's the AND gate. Second one, OR gate. So here the output of OR gate is true if and only if at least one of its input is true. OR gate performs actually logical addition. The Boolean expression for OR gate is Q is equal to A plus B. Okay. So the symbol is given over here, and the truth table defines that if inputs A, B are 0, then output will be 0, and for all other inputs 0, 1, 1, 0 and 1, 1 combinations, the output will be 1. Actually, it is also called as exclusive OR gate. So that's the OR gate. Then the third one, that is NOT gate. So the output of a NOT gate is true if and only if its single input is false. Actually, a single input is given to the NOT gate. So if the input is 0, output will be 1, and if input is 1, output will be 0. Actually, it performs a logic invert or complementary function, and its Boolean expression is Q is equal to A bar. And the logical NOT gate is also called as logical inverter. So that's the fundamental gates. Next we move on to the compound gates. First one, NAND gate. The function of a NAND gate, or NAND gate is also called as NOT AND gate. It is a combination of AND function and NOT function. And the Boolean expression is Q is equal to A dot B whole complement. So the truth table will be in such a manner that if both the inputs are 0, output will be 1. Inputs are 0, 1 and 1 and 0 combination, again the output is 1, and if both the inputs are true or 1, the output will be 0. Just a complement of that of the AND function. And the next gate, that is NOR gate. The function of NOR gate is a combination of OR function and NOT function, and the Boolean expression is Q is equal to A plus B whole complement. Okay. And in this case, only if the inputs are 0, A and B are 0, output will be 1, and for all other combinations, output will be 0. So it is the NOT function of the OR function, that is Q is equal to A plus B is the Boolean expression of OR function. It is just a complement of the OR function, that is a NOR gate. And next one, that is an XOR gate. The output of XOR gate is true if and only if either of its two inputs is true, but not if both are true. Okay, which means that if the inputs are of 0, 1 and 1 and 0, the output will be 0. If both the inputs are true or both the inputs are false, then output will be 0. And its Boolean expression is Q is equal to A XOR B is equal to A bar dot B plus A B bar. So that is the Boolean expression. Next one, that is XNOR gate. So XNOR gate is inverse of XOR gate. It is a combination of XOR gate and NOT gate. And Boolean expression is Q is equal to AB whole complement plus AB. That is, if both the inputs are true or false, the output will be 1. That is true. And for the combination 0, 1 and 1, 0, output will be 0. So that's about the gates. In these gates, NAND gate and NOR gate are called as universal gates. Okay, so that's about the basic of digital logic. Now here provided a simple objective test just for your self-assessment. Go through it. So question number 1. Which among the following is a universal gate? Options: AND gate, NAND gate, NOT gate and XOR gate. Answer is simple: NAND gate. Second question, the output of which logic gate is true if and only if all of the inputs are true? Options: AND, NAND gate, NOT gate and XOR gate. Correct answer is AND gate. Question number 3, which among the gate performs logical addition? Options: AND gate, OR gate, NOT gate and XOR gate. Correct answer is OR gate. Question number 4, which logical gate is also called as logic inverter? Options: AND gate, OR gate, NOT gate and XOR gate. Correct answer is NOT gate. Question number 5, the Boolean expression Q is equal to A plus B whole complement represents which logic gate? Options: NOR gate, OR gate, NOT gate and XOR gate. Which is the correct answer? NOR gate. So which among the following expression come under commutative law? That is the next question. And options: A plus A is equal to A dot A is equal to A plus B is equal to B plus A and A plus AB is equal to A. Correct answer, commutative law states A plus B is equal to B plus A. Question number 7. Which among the following expression is true according to identity law? Options: A plus 1 is equal to A plus 0 is equal to A dot 1 is equal to 1 and A dot 0 is equal to A. Correct answer, A plus 0 is equal to A. Now which among the following expression is not true? Options: A plus 1 is equal to 1, A plus 0 is equal to A dot 1 is equal to 1 and A dot A is equal to 0. So correct answer, A dot 1 is equal to 1. It is not true. Question number 9. Which among the following expression states De Morgan's theorem? Options: A plus B whole complement is equal to A dot B, A plus B is equal to B plus A plus B whole complement is equal to A dot B whole complement and A plus B whole complement is equal to A complement dot B complement. So which is the correct answer? Last one, that is A plus B whole complement is equal to A complement dot B complement. That is the De Morgan's theorem. Now last question, that is the sum terms in the standard pose form is called as options: min term, max term, product of sum of products. Which is the correct answer? Max term. Okay, so that is a simple objective test just for your self-assessment. So that's it. So thanks for watching the video. Hope you have got some information about the fundamental digital logic. So watching more videos and hitting your suggestions, please subscribe our YouTube channel Jnana Learning. Thank you so much.